So let me start by thanking Klaus, Clemens, I saw here, Mariana, well, wherever she is, thank you so much for inviting me. I really appreciate to be able to present our work, which is, well, not even fresh out of the press, fresh somewhere, but on the archive at least, which is about quantum sensing in the context of quantum gravity. And I also want to very much thank Andrew for this really fantastic workshop so far, very, very stimulating. Look forward to your next book. Okay, so here I want to talk about detecting single gravitons with quantum sensing. But before I get there, I just want to have a very brief marketing or a propaganda slide just about a group in general and different type of topics that we do. For me, in many ways, my academic journey started here in Santa Barbara. I was an exchange student and I bumped into Dirk Baumeister, who does experiments with optomechanical systems to test Penrose's gravitational collapse theory. And I was fascinated back then, 15 years ago, that you could actually do experiments about the quantum nature or alternative theories about gravity in tabletop experiments. So it's been very influential, and I feel like, you know, it stayed with me ever since as a theorist thinking about these directions. So today in my group, we study kind of the combination of quantum foundations, quantum sensing, and gravity from a theoretical perspective, and relatively agnostic about systems. So whatever could be useful. And so kind of this propaganda slide is because we actually also have, you know, open postdoc and PhD positions. So in case you have somebody who's interested in this direction, you know, let them know. Just as a very brief overview of different type of topics, some of them, we work quite a lot, and we did with my collaborators over the years on what we call proper time interferometry. I think it was mentioned a little bit on Monday. Which I missed, unfortunately, where it's about testing the classical gravity as a background, but where new effects arise on quantum probe systems. And in many ways, this is connected to kind of the quantum version of the mass-energy equivalence. And so we study kind of new effects that arise there, entanglement that we showed, and decoherence, and so forth. So it's been a you know, very rich line of research that is now gaining more attention, which is very nice to see. Then another aspect is test of quantum gravity, namely what kind of signatures of possible quantization of gravity could we see, or maybe even new physics that might arise because of quantum gravity that we would be able to probe in tabletop experiments, or at least constrain in some way. So it's a little bit like a high precision frontier, but not for beyond standard model physics, but beyond but for quantum gravity or new physics there. So there's different directions we explore, and caveats and loopholes, of course, as well. Another direction is applying quantum optics theory to cosmological questions. And one thing, for example, we find close connection to what we heard last talk, last but one talk, many others, this what's called in atomic community, this one twist squeezing. So we apply something similar, this Yerkes-Stoller Hamiltonian nonlinear one, that one shows that actually dark matter particles, such as light, ultralight particles, because of their self-interactions, they're actually constantly self-squeezed. And so this might be relevant for searches for dark matter, because there is unavoidable squeezing that takes place all the time. And I have to think about if two-axis squeezing might play a role there too, I don't know. Other topics are just kind of optomechanics, atoms, how do we do measurements, QND measurements, and squeezing by projection, or atomic metasurfaces, in what novel regimes basically of quantum mechanics can be explored. And then finally, the final thing I just want to mention briefly here is also the research agenda of studying how we can use novel quantum technologies for different types of gravitational wave sensors. One work using atomic clocks, which was with Shimon Kolkovitz, Juni, Misha Lukin, Ron Walsworth, where we showed that there is another approach you can test for gravitational waves, in many ways complementary to atomic fountains. And I want to also agree with James from his last talk that indeed his paper from 2017 showed a really nice and deep, kind of clear understanding of what is actually really at the core of it. And then another work was Swati Singh, who was here, and Keith Schwab, on using superfluid optomechanics as a new kind of quantum resonant detector. Now, I mentioned that kind of just as an overview, but in many ways, the talk here is a combination of two of these topics that, in principle, we didn't think have anything to do with each other, but they do, namely the test of quantum gravity phenomenology and the ability to measure gravitational waves with novel systems. And so the core topic here that I want to discuss is, can gravitons be detected? And of course, the conventional answer is no, and there's very good reasons for that. So LIGO, if you compute, LIGO detects basically a classical gravitational wave that consists on average of 10 to the 36 gravitons. Okay, so it's even that is hard enough, took 50 years. So you really, it's 30 or 6 orders of magnitude better sensitivity you would need in order to detect a wave consisting of a single graviton. The same statement can be phrased as that the graviton absorption cross-section is on the order of kind of Planck length squared. So it's just extremely weak interaction. They just pass through any detector and don't interact. And so if you can think about energy scales where gravitons might be relevant, you really need some incredible colliders way beyond anything one can imagine. Okay, so that is all of that is true. And still, here I want to present and convince you, at least by the end of the talk, that yes, indeed, it is actually possible to detect single gravitons. And this is basically this talk is a summary of this paper from August this year. Okay, so let me just go back. If you open Weinberg's book on gravitation, there's a very nice chapter, I think chapter 8 or so, on kind of quantum mechanics and gravity. And what he does is he computes what the transition rate is of an atom, a quadrupole transition, with the process of emitting a graviton. Okay, and he goes through a computation which is very similar to just the standard quantum optics computation, except your interaction is such that the quadrupole matters, but you can just do the calculation straightforwardly, and you find a transition rate, say from 3D to the 1s state, and you find a number, so you can compute it. It's not a problem because we can deal with linearized quantum gravity. We know it's this since Bronstein, and then ever since many people looked at that. There's a small mistake, so then Born and Rothman, they actually looked at it even more detail. The mistake seems to be just some numerical factor, but the rate of single graviton emission from an atom is something like once in 10 to the 40 seconds. Okay, so needless to say, Weinberg concludes there is no chance of observing such a transition. That's of course true. Okay, so that's a nice computation, but it's not relevant in any physical sense. Now, it means a typical quantum system emits a graviton once in 10 to the 40 seconds. Age of the universe is maybe 10 to the 18 seconds. So, it's just to show that the scales are such, there's no hope to even think about it in this sense. So it's really, this absorption cross-section is irrelevant in quantum mechanics. And so it was even speculated, there's a nice paper by Dyson, kind of hand-wavy, but still, maybe it's never even possible for all practical purposes to have any single graviton detection or signatures. Okay, so is that true? Well, in this talk, I want to show that one can modify this reasoning and actually find a regime where it is possible to experimentally detect a single graviton. So it's 3 modifications that we make in order to highlight that it's actually possible to observe it in experiments that could be designed. Okay, the first modification is we don't need to look at atoms. So that's a typical thing which differentiates quantum optics from other fields. Atoms are nice, but there's plethora of quantum systems that we can now control, manipulate, and sense at the quantum level, which operate at completely different scales. So we can look at quantum systems which are very massive, for example, or have other scales. The second aspect is we can focus on stimulated emission and absorption, and not the spontaneous case, and the stimulated emission absorption of single gravitons. And then the third aspect is we also introduce quantum sensing, in particular quantum sensing of quantum jumps, individual quantum jumps. So not some kind of average measurement, but individual events that we focus on. And when all 3 of these conditions are met, indeed one can achieve single graviton detection, which I'll outline here how this works. Okay. So first, A is the focus on something else than atoms. In particular, what we are interested in are macroscopic quantum systems and the interaction with a macroscopic quantum system. And this was in many ways inspired by my work before on optomechanics with superfluid helium, which is an inherently quantum system. And so there is actually the focus on optomechanics here, a nice overview, where you have a huge scale of different masses that are accessible quantum mechanically, and we can prepare quantum states. I think recently really prepared quantum state of the center of mass motion of a LIGO mirror, I think a year or two ago. So the key here is that we have the ability to prepare and measure quantum states in macroscopic systems. And that matters for gravity because we can scale up effectively the charge, which is the mass. We can scale it up to a macroscopic scale and still talk about quantum phenomena and discuss and observe them. Okay, so how does this interaction look like? The linearized interaction, one can write it in terms of this interaction Hamiltonian that couples the stress energy tensor to this linearized perturbation over the flat Minkowski metric. This is a nice way to actually do something like quantum optics because there's a Hamiltonian that one can work with. And now what we look at is a system that doesn't consist of a single atom, but n atoms. And now from first principles, one can derive what this interaction is between these systems. I just very briefly go through it. So we have like n plus 1 atoms just for the boundary conditions, each of mass m and each a distance a. Then one looks at the local frame. Then the gravitational waves effectively acts effectively as a tidal force. So it kind of squeezes this thing periodically. You know, we couple it to the energy of the system. And so we get this interaction Hamiltonian. One can change variables for a collective degree of freedom, such that we can look at collective modes. And what one finds is then in the end, there's an interaction Hamiltonian between a collective degree of freedom of this overall n atoms, which scales with both the macroscopic mass and the macroscopic length of the system, and also contribution, which is basically just the n individual atoms. So each one of them individually. So this is a subleading term. So basically each atom gets squeezed, but also the overall mode also gets squeezed by a gravitational wave. And so we get n individual quadrupoles from this term, and then we get, I guess, also get collective modes. And this interaction now, its effective charge is scaled up by both the macroscopic mass and the length. Okay, and then we can quantize this Hamiltonian as well on both the matter and the gravitational sector, and then we have this interaction between them, and it's, you know, a bilinear interaction that we know how to deal with. Okay, so how would you know, what are the numbers for such a system? If you look at the typical graviton transition rate from some initial to final state, just using the Fermi golden rule as the simplest case, we use now this interaction Hamiltonian of the macroscopic system, not of a single atom. Anyway, one can compute it. It depends just on some system parameters, such as the density of the system and the speed of sound. And then what one finds is, just for an example, niobium cylinder. If one uses that, which was used to be a gravitational wave detector actually in Australia, just plugging in the system parameters on the order of a 1 meter scale, one gets that the spontaneous emission rate is 10 to the minus 33. Okay, so it's a different rate, so it's much better, like nearly 10 orders of magnitude better than Weinberg. So it's already pretty good. You just jump by 10 orders of magnitude. It's not enough. So both of these things I think are actually important, but it's not enough. But it's it's already very different. Okay, so then we do B. Okay, so spontaneous emission is not feasible, but what about stimulated emission and absorption? So we can then instead compute the stimulated emission rate. Here, quick and dirty on this slide, just using again Fermi's golden rule. If you do that, well, you get some outcome here, which again depends just on the parameter of your bar and the modes. So basically on its fundamental frequency and the mass. And this alpha square is effectively the classical classical amplitude of the gravitational wave. Okay, and then we get a stimulated rate, which depends on this amplitude of the gravitational wave, and effectively just mass and speed of sound of the system. And then if you take an example like aluminum bar, like Joe Weber had at the very beginning of gravitational wave detector development, if you plug in something like 2 tons and it's a system parameter, and you take now a gravitational wave amplitude from a known source, now we know what the sources are, like the first detection of gravitational waves, what you get is that the stimulated rate is actually 1 hertz. Okay, so it means there's 1 graviton emitted and absorbed on average per second. So the timescales you get are actually very normal. And the reason for that is precisely because the gravitational wave interacts so weakly. Even though it consists of so many gravitons, the interaction is so weak that on average, you actually get human scales. Okay, but this is kind of just as a motivation. So now we dive in a bit more deeper. First of all, there's a direct analogy now to what we're talking about. When we talk about stimulated emission, we're going back all the way to the roots of quantum mechanics, basically the first experiments that showed it, which was about stimulated emission. So the photoelectric effect is really something that was the first evidence for Einstein that showed that there's a quantization for matter, and that was the deep insight of Einstein, also of the electromagnetic field. So that is a stimulated emission process. And Einstein postulated in 1905 that if we want to believe that there is energy conservation between matter and field, we must also believe that there is a quantization on the field sector. Yes?
If you drive a system classically, then you have the same resonance condition and the same observation in terms of the
Yes.
but it's not really proof that it's quantized.
Yeah, that's exactly right. Exactly right, yeah. And that's in fact, that is precisely what I'll say more about it later. And the words also used is precisely right. So we make a very careful distinction about proof of quantization versus detection. So there's two different things. And this is exactly the same as in the early days. So in fact, a proof of a photon was, came later by Clauser and later by Aspect, 80 years later or more. But still, at that time, if you want to assume something reasonable about your theory, namely that it should be a real theory that has something like energy conservation, it's very hard to go around the fact that the field has to be quantized. That was disputed for a long time, but finally Einstein prevailed that this is the view. Anyway, so what we're doing here is in many ways very similar to these early days of quantum mechanics, except now around an electromagnetism, we're discussing it for gravity. So, of course, I mean, this is a very simple slide. We all know there's stimulated emission of photoelectric effect. There is photons that coming in with certain energy, and this energy excites electron out of the conduction band, and then it has a certain maximal kinetic energy. And this maximal kinetic energy can be measured by the applied stopping voltage, just to see what comes out. And this is a famous, I think the first it was measured by Lenard, and then later famous experiment by Millikan, showing that, you really have this linear scaling, and so you extract h bar. And even at that time, if you read Millikan's paper, indeed, he says, well, yeah, this is very nice. Still, it's not, of course, proof that there's any photons. It's complete nonsense. And so, but over time, people kind of were convinced that this is the, let's say, the easiest way to think about it. Okay, so this is the analogy, except we don't have neither a source that you can just control, nor do we have some stopping voltages or something like that for what we look at. So what do we need still? So we want to do something like a gravitational photoelectric effect. And at the core, what it really is just about is the discrete exchange of energy. We literally just want to see that h bar omega is exchanged between those two. And so how we would see that is, well, we can apply modern quantum thinking or sensing, namely instead of averaging or looking at some kind of classical observables, we can try and monitor a single quantum jump in our system. If there is a single quantum jump in the system, that means that this event, really only a single graviton was absorbed if it's on resonance. Okay, so it's about the exchange of a single quanta of energy between matter and the impinging wave. And so what we want to do is we need to be able to observe a single quantum jump by a discrete amount of energy. So it's not sufficient to measure a position or something like that, because you always average and any value is possible, but you do want to measure energy and make sure that it's really only a discrete change. If you can correlate it to the impinging gravitational wave, that was an absorption event from the gravitational wave. Okay, and so we call this the gravitophononic effect versus photoelectric effect. Okay, so the C condition that we needed is you want to be able to monitor quantum jumps. And oh yeah, I think I learned from Peter yesterday that if you mention the Möllmer-Sørensen gate, you get an extra minute. So, yeah. So I hope that's true. But I just want to show there's a really nice experiment from Serge Harosh's group. And of course, there's many, many experiments since, basically doing QND measurements where you can continuously monitor, in this case, the field, electromagnetic field in a cavity with a Rydberg atom, and you couple to it through energy. And then you can basically monitor what, you can just reconstruct what Fock states are in. And here in this movie, it's just a simple case where initially there's a coherent state. It very quickly loses coherence and then slowly decays down, that they can monitor through just looking at the excited or ground state of the atom. Oh, and then it doesn't work anymore. Oh yeah, here. So this is basically the field of the state of the field, and then you see how it's, you can really measure continuously single Fock states, and over time they kind of slowly decay and then go basically to the ground state, and then nothing more happens. So it's a nice just demonstration that you can kind of continuously do QED measurements where you couple to the energy of a system, and you can reconstruct this kind of energy states. Okay, so that's what we basically want to do. That's what we need here, because what we want to do is we don't know when a gravitational wave comes. We want to just have a system that we have in some well-defined energy eigenstate, ground state, ideally, or probably easiest, and then you just monitor it. I mean, but then you monitor it. So you do some kind of QED measurements continuously, weekly, such you don't disturb it too much. And you can write down what measurement operator you need, and you kind of with an ancilla, and you constantly measure the ancilla, but very weakly, such that you have like an evolution both due to the measurement and from noise as well as impinging gravitational wave. So you get kind of a state evolution, which includes measurement now as well, but the measurement is coupling to the energy of the system. So that's very different from normal bar detectors that all use transducers where you couple to position. And position won't help you because, yeah, you can measure, you can reconstruct energy, but any value is possible because you average. For us, our key is we just want to say, look, it just jumps by one amount, and then that kind of is reasonable that was a detection. Okay, so the question is, can we detect a single quantum jump from gravitational waves? Now, the issue is I showed you before these rates, and I said it's quick and dirty. You can't work with them, of course, because these rates is averaging long time, and it's, again, this kind of averaging thinking. We want a single event and a single condition. So, in fact, if you look at the sources we know, they're very transient. So they are, they're changing frequency, they're chirping, and then they're stopping. So you cannot use any of these rate equations to get any reasonable amount, number. And so what I showed you before is just kind of as a first hint of what happens. So instead, and I don't go into details, but you can solve this dynamics exactly, which is not surprising because it's a harmonic oscillators, bilinearly coupled. So you can solve it exactly what happens in a direct analogy to the quantum optics case as well. And so what you find is that if you find the dynamics, just a unitary evolution due to this Hamiltonian, and in fact, indeed, we already assume, let's say we wanted just for the case where our gravitational wave has, is basically a huge coherent state, then it's even easier. So we use in this kind of semi-classical language, you can find the exact dynamics, and what you find is that it's effectively just a displacement operator with a specific displacement strength that depends on, so this G is this whole prefactor on some time-dependent shape of your gravitational wave, and what you get is, it's direct analogy to, Glauber's, of course, work, where he showed that coherent states are created in matter if there is this interaction with the field. And so this is what happens if you have a detector in a ground state. The gravitational wave will create a coherent state of the matter sector. But what we are interested in, just to say there's a very specific amplitude of it, and this amplitude depends what we call this chi parameter, which is a complicated function of your gravitational wave, amplitude, time dependence, all of that. But that's kind of, none of that matters, it's just a coherent state, it's just you have to compute what this is for a specific source. Okay, so this just captures your gravitational wave profile. And then what we're interested in is we want to monitor a single transition. Okay, so we just want to monitor the transition, say from 0 to 1, and you can of course find that exactly. You find this depends, on this beta, and that means that the gravitational wave came in and a single excitation was induced, and you can find how do you maximize the probability. So what we really want to do is we don't want just a gravitational wave detector. We want one that maximizes the probability of the transition from 0 to 1. So it's basically a very bad detector. Like usually you want a very big excitation, but here you don't want that. You just want a single transition, and the maximum probability you can get for that is like 37%. And then you need to tune your parameter to get that. Okay, and so I'll show just in a little bit what the parameters would be. So you get this Maxwell transition probability for this type of detector. So the basic idea is you have gravitational waves coming in, there's stimulated emission process, It's very bad. It's a very bad emission process, but it's so many gravitational waves of them that basically there is a probability that there's one event, not an average, but one event which excited a single energy, a single energy excitation. So you get a change by h bar omega. Okay, and that depends now on your gravitational wave profile, of course, on your detector itself, but also on the gravitational wave profile. So now you can look at what gravitational profiles do we actually have, and what numbers do we get for this. And so we can find the ideal detector mass that's optimized specifically for this, maximizing this probability and not some higher excitation. And it's given by this in terms of system parameters and this wave profile. And then you need to compute it. So it's a complicated function. What is this? Well, it depends on the strength, duration, and the wave packet and so forth. But what we can do is we know now what the gravitational waves are, for example, in the LIGO band. We can just take the data, so you can numerically find what this is, or you can find some analytic approximation, which actually works very well for this binary star merger. So we did everything analytically as well. You find a very specific expression that depends on this kind of binary source chirp mass of your source. So inversely proportional. And then it depends also on the frequency of that. And this approximation works when it's a slow transition through resonance. It's basically a resonant detector, and it basically just resonates up when your gravitational wave chirps through the resonance slowly. Okay, and with that, this is kind of just a quick summary of different system parameters you may want to consider. So the first four columns, so this on the top are possible sources, and here are like detector functions. And so sources, for example, the most interesting source we found is the neutron star merger. That actually gives the best case scenario. For this particular case, it's in the in the 100 Hertz range. What you get is that a detector on the order of 20 kilograms is actually sufficient to detect a single graviton. So it's a very simple detector in some sense. The complexity, of course, comes in that you have to ground state cool it and then continuously monitor the excited energy. So it's, of course, extremely difficult, and you need high Q factors, low temperatures, and so forth. But in principle, you have some sources for which this is reasonable parameters that come out. And then you have also, at higher frequencies, you could have some speculative sources, maybe new physics or sources we haven't detected. Also for those, there could be, some interesting, more short-term, maybe experimental searches that one can do. Okay, and then finally, so I just want to highlight that, there are some reasonable parameters that actually come out. And okay, so you can simulate this experiment. How would it look like? You don't know when the gravitational wave comes, and so you have to reinitialize it. We just basically simulate this continuous monitoring, that you have like the ground state on the first run. There's a duty cycle. You have to recool it after 40 seconds, and then redo it. And then finally, there is a gravitational wave, which is this short pink window. And then you can find that the probability of being in the ground state goes to 0, and the probability in excited state goes to 1. But that's this one particular realization, which only happens, with 37% probability. And here, this is including noise. Okay, but the point is, you combine this ingredient, you have macroscopic quantum systems, stimulated emission, quantum sensing of individual jumps, and so somehow this is pictorially the thing. And then finally, I want to mention the main ingredient also you would want to use is the correlation with the real detection events. You don't have any control over your source, and instead you can correlate with other detection events such as LIGO that confirms, hey, there was a wave, it has this frequency and so forth, and if that corresponds to your, kind of single graviton h bar omega transition, that gives a strong indication that this is really due to the impinging gravitational wave. So it's the correlation with other types of detectors which is really making it possible. Okay, and just to make this quick analogy, so instead of electrons, we're looking at acoustic modes in massive detectors, analogy with the photoelectric effect. Then we don't have any controllable source, but instead we wait for some sources. There's all-time sources, such as neutron star mergers, and you correlate it then with LIGO to confirm what the source actually was. So you kind of just have to wait a long time. And then instead of measuring voltage, you look at quantum jumps. So you monitor quantum jumps to see that you really had h bar omega. That's the key. Okay, and then the last, this extra minute of the, I just want to mention exactly what Klaus said. Namely, of course, one has to be careful. This is not a proof of that they're gravitons. It could be other theories that also could reproduce it. So this result is obtained, can be obtained in the semi-classical limit, just as the photoelectric effect. Okay, so the modern view is, well, we know photoelectric effect is produced by stimulated emission through a coherent state. That's very different than a Fock state. So really, to show there's a Fock state of the field, you would need completely different measurements. Anti-bunchings, Hongo-Mandel effect, negative Wigner functions. So these are the type of modern proofs of the quantum nature of the field. What we're talking about is not of that form at all. So it's not like the modern version of quantum optics. It's really the early version. But for gravity, that is already something which is way beyond, I think, that what kind of maybe currently is considered possible. So it's kind of the early indication that if you believe energy conservation, you must have gravitons as well. So we cannot detect the quantum state of the field. So it's not about that. You can't do that. But what you really detect is the discrete exchange of energy. So h bar omega, that's what you want to look at. And you need a resonant detector. But semi-classical dynamics, even when you have that, if you include energy conservation, then it already includes, you could do some neoclassical theory or something like that. But all of that always includes, the exchange of energy in discrete packets. So whatever the theory there is for gravity, it must include this discrete energy exchange if you show it in this type of experiment. Okay, so again, analogy is not a test of QED, so it's not a test of quantum gravity, but it's evidence of it, kind of, an early of it. Okay, and I also want to mention, in fact, the semi-classical limit to me is still a little bit cheating because you get that after you know QED. So we do quantum optics as a limit of QED where we just replace hats by no hats. But that's not a real theory. And in fact, that's not how people argued, that's not how people argued in the early days of quantum mechanics either. It's not something that comes from Maxwell's equations. So you do need somehow this to account for this discrete change of energy or give up energy conservation if you want to build a real theory. Okay, so with that, just a quick summary. So gravitons can be detected is kind of our message here. What you need is macroscopic quantum resonators that are in the ground state. You rely on stimulated single absorption events. You need continuous sensing of energy in the quantum limit, quantum jumps. And in fact, this weak interaction with gravity is precisely what makes it possible. So it's kind of inverted a little bit. It's, it's weak, so it's bad, but actually for this case, it's good because then you really get single events and not like, million gravitons on average or so. Okay, and this can be achieved with realistic parameters. So for theorists, I want to say, I expected actually, whatever black hole masses. No, you get like 20 kilograms, but you do need to be able to, monitor the energy of such systems. And I think the current record, I think is in Zurich is something like a milligram masses or something like that, where they really have dispersive coupling to the energy and can measure Fock states. So, it's a few orders of magnitude away from the masses you need here. And again, it's not a proof of quantum theory of gravity, but it's a detection of gravitons. Okay, and then with that, I want to thank, of course, my whole team, and especially Jermaine Tobar and Thomas Beidel, my students, and Srinath Manikandan, who was the postdoc on this project. Thanks a lot.
Start over here. Very nice, Igor. Can you define for me what the graviton is?
Yeah, it's a discrete packet of energy of h bar omega. I think that's the best definition. It's a discrete package of energy of h bar omega. So I'm not talking about the graviton state or something, which would be the eigenstate that you always get the same answer, but it's this amount. Exactly. In this case, yeah, exactly. I'm not making any statement about any possible quantum field theory of gravity or something like that. It's just it's a chunk of energy that's discrete. It doesn't have any continuous value.
So,
right, but if the detector jumps up this way, it absorbs precisely that amount from the gravitational wave, or vice versa. So whatever it is. Sure, but it could absorb some other amount or something like that, right? I mean, it could absorb, 10 h bar omega or something like that, yeah, I mean, yeah. But that's what I mean, it's exactly the same as the photoelectric effect in the sense that you absorb this amount on the matter side, you conclude that, that's it. One way to think about it is this, let's say you believe quantum theory of gravity, you have H hat, then of course there's an exchange, you have A dagger B plus B dagger A in the rotating wave approximation. So there's an exchange, each absorption event here corresponds to a reduction in h bar omega on the side of the field. But that's what I mean, it's not a proof, it's not a proof that the gravitons exist, it's just if you believe them, you detect them. It's a click. Sorry? Sure, but it shows that you can detect them.
What is your black body spectrum for this, right? If you just apply Einstein's thinking, right, you now have an exchange of this nature. You've got a thermal bath of these things. You said that the rate was really small, but there's a lot of atoms in the Earth, right? So what's your rate coming from the Earth from those numbers?
Yeah, I mean, it's a good question. You have this black body emission, should go 1 to 1, like from the Planck spectrum but it's extremely small, like the black body emission. I mean, here the gravitational waves are violent black hole mergers that emit tremendous amount of energy. So black body emission of gravitons exists as well, presumably, but it's just extremely weak.
Well, since the mic is here, I sort of asked a question. I didn't quite understand. So your mass wave bar, whatever you call it, you rely on its own quantization as a harmonic oscillator, right? You cool it to the ground state. So the only way to excite it, doesn't matter whether it's graviton or other excitation, it's always discrete excitation. So yeah. Unlike the photoelectric effect, it's actually looking at the threshold. So I'm not sure how, by looking at a quantum jump in a bulk bar with the quantum jump would actually demonstrate that whatever the excited is quantized.
True, so it's not an exact analogy. So you have threshold, but there's nothing particularly special about the threshold or the harmonic oscillator has discrete levels, and that's the whole point of the photoelectric effect, that you can only absorb discrete packages of energy. So just in the photoelectric effect, you have to work harder. So you need also a threshold and so forth, and then you go into the continuum. Here you have discrete levels kind of already given, and you just kind of monitor them. But you can of course also do some unharmonic oscillator. I mean, you can in principle look at it in an unharmonic case, so you really have only 2 levels. Either way, yeah.
I thought that to see the threshold, you would need to see excess energy beyond the excited one single quanta in the test detector to see the discretization of quanta excitation like photoelectric effect. Because otherwise it's more analogy to atomic level excitation, harmonic oscillator excitation rather than photoelectric effect, because you're not coupling to a continuum.
Sure, it's a harmonic oscillator excitation, exactly. Just the point is that the one thing you want to see is the discreteness. That's kind of the only thing. You just want to see discreteness in your system. So
we can take maybe, I don't know, we have some time for a few more questions, so yes.
I guess you really need a continuous variable that is coupled to the energy, right? So that when you measure the continuous variable, you see discreteness at the outcomes. Right. And then that's a proof that there's discreteness. So I'd like to learn more about the physical system that does this continuous energy measurement.
That's a good question. We didn't go into that. Like ours is kind of a very basically ancilla, some continuous variable ancilla that you do some homodyne measurement on or something like that. But there's, I mean, people implement that with like some dispersive couplings, usually maybe.
But people have been trying to do that in optomechanics for many years, and they never got around to demonstrate it.
Exactly. Yes. So in optomechanics, you have the field coupling maybe to energy, like in Jack Harris group and others. The superfluid helium maybe as well.
But they kind of gave up on it, I think, right? They never demonstrated anything.
Yeah. Well, let's say in other systems, there is coupling to energy demonstrated. And that's in the superconducting circuits, basically coupled to some phononic modes. So there is actually demonstrated internal acoustic modes, quantum acoustic modes, and coupling of energy to them. So really a Q&D measurements of them. That was used with superconducting circuits. That's what I mean with even Chu's group, I think, Rob Sherkopf. So there's a few ideas, but yeah, that's the hard part. Let's say if I wanted to compare to other approaches to test quantum gravity with loopholes, all of them rely on usually some superpositions or some kind of quantum state preparation. Here, the quantum state preparation is easy, just ground state cooling, but the challenge is then instead the sensing part. You have like quantum sensing instead. That is very hard.
Yeah, I had the same question. In a related issue is that, of course, when you measure, suppose you can monitor the energy continuously, you're also cooling the system at the same time, and so there's very mundane sources of excitation, like thermal excitation from the background, that you have to be able to kind of distinguish from your background, from your signal. I imagine this gets quite tricky.
Right. It's a good question. I skimmed over that a little bit. That's what we did. We kind of compared it to Brownian motion, specific system parameters like millikelvin cooling, which is like, adiabatic nuclear demagnetic. So very hard, but, maybe 10 millikelvin and a half. And then we simulated that for Brownian motion. That's how we got this duty cycle of about 40 seconds or something like that. So every 40 seconds you want to recool. And so this simulation is done with Brownian motion. And so indeed, kind of slowly, there is some probability of excitation even without the gravitational wave. You just kind of recycle. You also want to cross-correlate to LIGO to kind of exclude such events. But then if you do have a real gravitational event, it looks very different in principle.
Yeah, the other question I had is about, in terms of monitoring the energy. I'm just wondering if you could do a sort of a transduction from the gravity wave into something like a phononic mode of your big aluminum tin can, right? Can you kind of excite some kind of phonon that you would be able to measure using some other kind of detection scheme? This would also be interesting, I think.
Yeah, I think this is the right question. We don't have answers about how such a detection you would have to implement depending on the system, but I would assume you need access to these acoustic modes. So maybe coupling different modes together, it might be the right way. Like optomechanics does that also a little bit, yeah.
Then I see also Mariana has a question on Zoom, so we can maybe take that one.
Thank you for a very interesting talk. Can you hear me okay?
Yes.
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 I'm trying to see if I understand correctly. So you built a detector which would be resonant with specific frequency of gravitational wave, and I understand, and you're saying that this neutron star with 100 hertz or so seem to be good. And then you wait for gravitational waves, and you have to continuously essentially cool your system and hoping that exact gravitational wave frequency will come. So if that's a correct understanding, how resonant is it? Like, for example, if it's not 100 hertz but 95 hertz, would you still be able to detect it? Or maybe I'm just misunderstanding what you're trying to do.
No, you're exactly right. I think that's exactly right. So you kind of pre-select what sources you might want to do. And that's why this computation shows the neutron star mergers are kind of very nice because they're very slow. They take a while. And I think we were actually even a bit conservative here. It might do better. And indeed, the whole thing of how resonant you are, you're actually not as resonant. There's a lot of off-resonant excitation too, which is captured by this chi parameter I showed here. And so this resonance condition is captured by this chi, how the resonance is built up. So you could be a little bit off, but you have to remember that these gravitational waves chirp. So they change their frequency all the time. So they come through your resonance window, basically, and then go through over time. It's just that the neutron star merger do that slowly, and that's why it's nice. So even if you're 90 hertz or 110, it will still be nearly just as good. It's just there is some dependence on the frequency. But your gravitational wave chirps through. So it's not one frequency. It's like basically, one frequency that changes over time.
Oh, okay. And then the second question, it sounds like your method, what it actually detects is energy deposition. So what if you, for example, have 100 hertz dark matter, wave, would it detect that as well?
I mean, if it couples through the same way, if it couples to like phononic modes, I guess you could. It's just a resonant detector. It's just here in particular, we have this, H mu nu, T mu nu coupling. You could have other sources that could couple and noise. That's absolutely right. That's why I feel like the fact that you can now cross-correlate with other real detectors kind of helps you through this event. But you're right. I don't know if there's some exotic dark matter models that would couple to like acoustic resonators. Then they would do the same.
Thank you.
Okay, so I think in the interest of time, we'll have to move to our next speaker, but we can certainly have more discussion during the break.